Yeah, thanks, Lotte, for letting me know. So I checked the other the talk aggregator and seemed fine. The CS theory talk. I see. Okay. Okay, I'll keep an eye out for that next time. Thanks. Okay, I think we can start, Magnus, if you're okay with that. As people continue to come in, I'll admit them. Okay, so everyone, welcome to another DIMAP seminar. As usual, the talk is being recorded, so please remember that. Feel free to unmute yourself and ask questions, or feel free to enter your questions into the chat. The chat is again public, so please do not share any sensitive information. So without further ado, it's my great pleasure to introduce Magnus Wahlström from Royal Holloway, who is our speaker today. Magnus is an expert in parameterized complexity and constraint satisfaction. And today he's going to tell us about some exciting recent work in the intersection of these two topics, and which will appear at SODA 2021, if I'm not wrong. So Magnus, welcome, and over to you whenever you're ready.
Thank you. Yeah, so more accurate, I will present result in a framework or a method of solving graph problems, FPT, and the CSP applications are kind of a sideshow. So there was solving hard cut problems by flow augmentation, the joint work with Eunjung, Stefan, Kratsch, and Marcin. And as everyone said, this is accepted for SODA. So, is this even working now? Okay. So we're talking about cut problems. Obviously, everyone knows the tractable min cut, but there are several different variations of cut questions you could ask, which make them be hard. Some of the more basic ones, like multi-way cut, is if you have at least 3 different terminals, you're asking to cut the smallest number of edges to separate them from one another pairwise. Or multi-cut, when you have an arbitrary set of cut requests, like separate vertex S1 from T1 and S2 from T2 and so on, at the same time, the smallest number of edges. Or something I include for the sake of the historical view, bisection was a problem which turned out to be have a very interesting solution historically in FPT. Like you find a min cut with equal number of vertices on each side and the smallest number of edges. So I'll be talking about edge cut problems uniquely, and I'll be talking about FPT. And for the record, probably okay. So this is possibly everybody in the audience knows what FPT is, but just to be explicit. So we have a parameterized problem, means there's some kind of input k. So in our case, k will always be the solution size. And I'll try to, anyway. And the problem is FPT, if you can solve it in some running time function of k times polynomial. So this is fixed parameter tractable, and there's the positive case, and the negative case is when your running time is something again to the k. So cut problems have been a very big part of or FPT. It's probably it's probably 15 years ago since you might consider the first work on FPT algorithm for cut problems. It's like multi-way cut dimension was one of the first results, solvable in 2 to the order k times linear time. This is various different methods. Important separators is the key word if you're inside the area, but if you're not inside the area of FPT cut problems, then you just say there are several different methods for solving the multi-way cuts. Then there was kind of the next major milestone in some sense was multi-cut. The 2 groups solving it independently in 2011. And this was after it had been open for some significant time. So this again, they used different methods from a specific. I don't want to dig too deeply into which specific methods different people have used for this, because it would take too much distraction for somebody who's not already up to date in all of this. I just say multicut was historically much harder to solve, and it was solved by various interesting observations. And there have been several frameworks for solving cut problems in FPT time. I've mentioned two main results here. One by Marx, Sullivan, and Rascon, which is tree width reduction, which is the basic idea that if you can reduce, you can give it bounded tree width decomposition, which in some sense contains all ST cuts of size at most k, or all minimal ST cuts of size at most k, where the tree width is a function of k. And once you have bounded tree width, you can usually solve almost anything on that instance. And the second one, this is much messier to describe formally, but something like complete decompositions of the graph along all sparse cuts. Sigan, Lochtanov, Pilipczuk, Sakitsara. I'm very sorry, I forgot these. I forget the name of it. I forget who the K stands for in the second version. But yeah, this is a group of people have been working on various versions of this notion of decomposing the graph in a tree-like fashion across all sparse cuts. And of course, the idea being that once you have a sparse decomposition or a bounded tree with the decomposition of the graph, you can solve almost any problem by dynamic programming over that. Although I would say two things here. Bounded tree width reduction is linear time, but gives you tree width 2 to the k. And if you're going to solve an NP-hard problem on tree width 2 to the k, you're probably going to get 2 to the k running time if you just plug this in as a big hammer. And the second one, the complete decomposition, would take 2 to the order k log k time to do. So that's single exponential, but for the second one, the polynomial factor is up like cubic or n to the 4 as well. So you have to pay either in polynomial factor running time or in f of k factor running time if you're using one of these general big hammers. And all of this obviously was to contradict the natural reaction when an FPT person hears somebody say, we have a new framework for solving cut problems in FPT time. There have been many results of this type, but I do claim that what we're doing is interesting, a little bit different, and it can evidently do some things which were very, very difficult to do previously. So we'll talk about two sample problems. The first we call bi-objective ST cut is basically just ST min cut, so an edge cut with two budgets. One is a cardinality budget K, which is a parameter. And the second is your edges have arbitrary weights, and you're also finding a minimum weight cut subject to the cardinality bound. And the second is called coupled min cut. We'll talk about that problem a little bit later. The definition is it takes a little bit of time to get into. So the first one will be a simple illustration of our tools, although it is independently interesting as a question. And the second one will be this kind of showcased from the CSP world. So looking at the bi-objective ST cut, it's known it's NP-hard in general, it's strongly NP-hard. If you have two budgets and both are coded in unary, which is what strongly NP-hard means, you have a hard problem. It's also very easy to see that if K is equal to the ST flow, so if your solution you're looking for has to be an ST min cut, it's easy to also find the minimum weight ST min cut. So if you remember, capital W was the total weight budget from the previous slide. If each edge gets a weight of capital W plus its own weight, then, and your budget is K times capital W plus W, or some variation of this. If your solution consists of more than K edges than you would and W is not just all zero. You would exceed your budget if you break the cardinality bound. If you meet the cardinality bound, then of course we're chasing the lower order terms and checking our weight is at most W. And if you can find a solution of cardinality less than K, then that could be a very expensive solution in terms of the new weights, and you wouldn't be able to tell. Or rather, you wouldn't find the correct solution. So obviously, you cannot translate the bi-objective version, which is NP-hard, to just min cut. But the case of cardinality being max flow, the problem becomes easier. So this is going to be the goal of the framework. It's going to be to take problems like this one, bi-objective min cut, and translate it to a setting where the solution you're looking for has become a minimum cardinality cut between S and T. So I'm just going to give you, this is a simplified version, but it illustrates enough of what we're doing. So so flow augmentation, it's a randomized procedure which has some linear running time. It takes as input a graph and two vertices S and T and a parameter K. And the promise is that there is an unknown ST cut at the red edges on the left figure, which is not a minimum cut, but it's a minimal ST cut. And the output is we add the edges to the graph, like the green dotted edges on the right side, so that your old solution isn't affected, but the ST flow has increased until Z is now a min cut. So is it clear here what this framework does? I would put an asterisk on minimal because you can do some extensions of this, and if you read the actual paper, there's a little bit more complex formulation. But the entirety of the principle of what we're doing and why we're doing it is captured in just having Z being an unknown minimal ST cut. So it's a randomized algorithm, running time linear times something K, and probability is 1 in 2 to the order K log K. So the success probability depends only on the size of the unknown solution set. So if you just quickly observe what the algorithm for bi-objective ST cut is using flow augmentation, you repeat independently, you just repeat 2 to the K log K repetitions of flow augmentation to compute your new augmented graph. And then you solve your min cut problem as if Z is going to be a min cut. This we saw on the last 2 slides ago how to do. Out of these, you return the cheapest solution you found. The framework can be de-randomized, but we didn't dig into how to kind of optimize the success probability in the case of de-randomization. If you have to randomness, you can also just repeat this a larger number of times to decrease the failure probability. And as I said, well, maybe it's wrong to say this is a toy problem, but it's a very simple problem in its structure. And between all of these previous results, the 2 general frameworks I mentioned, both of them can easily solve by objective ST cuts. But as I said, the tree width reduction would give you double exponential running time unless you do something extra clever. And the lean tree decomposition framework, the second one could be called, would give you an n to the 4 factor instead of linear factor in running time. And okay, linear, I have to m log n because you use some kind of weighted max flow algorithms in step 2 of the loop, but hopefully everyone understands what I mean. Yeah, please send questions at any time. So just having this bi-objective min cut algorithm, there's at least one other problem you could also get for free. So again, people with a background in FPT might be familiar with the problem edge bipartization, that you remove K edges to make a graph bipartite. it happens that that algorithm is completely relies on doing a 2 to the order k repetitions of a min cut, and it happens this is compatible with the way we phrase this bi-objective version. So bi-objective version of edge bipartization would also be FPT with a similar running time as here.
Magnus,
Yeah.
so there's a question from Rupe. Rupe asks, connectivity augmentation is well studied. I think your problem is quite similar, right?
In some sense, but we'll get into the weeds this later. But it's critical that you don't do anything to destroy your solution, Z being a solution. So you have to be very careful to not accidentally augment so that you add an extra edge between the two components that Z separates.
Thanks.
So, okay, so now just a quick overview of the results. This is about my personal view of this paper. It consists of 3 components: the flow augmentation, the characterization for a CSP-type problem as announced, and an algorithm for a problem called coupled min cut. And this slide is to say that this problem was one of the weirder problems I had worked on, honestly. Like there were just so many iterations of trial and error and ideas that don't quite suffice, and let's have another round of some improvement. So for the record, this picture is from the Chrono Trigger RPG. And for anyone who's actually played it, there's a hidden message here that the real villain of this paper is the problem coupled min cut itself. Flow augmentation looks like it's going to be the main challenge, but it's actually quite doable, and coupled min cut turned out to be quite nasty. Okay, so more carefully, so we mentioned CSP, so this is kind of ways to formulate general like a family of problems. So we have a framework where you can express several different related problems. You're trying to study the complexity uniformly. Formally, you have what's called a constraint language. You can think of this as a set of, well, formally a constraint language is a set of relations, but you have some set of different constraint types. Your input is some formula as a conjunction of constraints of these types. And the question is there an assignment to the formula where at the most k constraints are false? So this is all in the Boolean setting. We don't have any strange variable domains. So variables take just the values true or false. So here's a few problems that can be captured as different instances of this family. If your language contains the 2 assignments, like a vertex should take the value 0, a vertex should take the value 1, and 2 vertices should take the same value, then this is basically an undirected graph cut. So if you have a graph with some vertices S and T, you get a formula saying S equals 1, and maybe the first one you repeat like k plus 1 times to make it too expensive to break. At the end, you have T equals 0, again repeat k plus 1 times to make it too expensive to break. And in the middle, for every edge of the graph, you have an equality constraint. And if you think about what this implies, it means we have to falsify constraints v1 equals v2, for example, corresponding exactly to a cut between S and T. So minimum cost solution to this instance will be a minimum cut in the graph. And without going into quite the same detail, there are some other problems which have been interesting in the FFT world, which are also phraseable in this setting. If you just have a single constraint saying x is not equal to y, you can get edge bipartization. Like the 2 values is vertex is placed on the left side, vertex is placed on the right side, and a false constraint corresponds to an edge within one of the sides. and almost 2-sat with the language is 2CNF. And last, this is a famous open problem called chain sat, where a constraint is basically a sequence of constant number of directed edges, let's say. So you have a graph, a directed graph. As a graph problem, the last one is you have a directed graph of vertices S and T, and your arcs are grouped into chains of length at most L as a constant, where for cost 1, I can break all the edges from x0 to x1 and from x1 to x2 and so on. So this is an open problem which has been formulated several years ago and which seems to capture something really difficult about directed cut problems. So in this setting, so the game is you want to be able to say for which choice of language gamma is the problem min-sat gamma FPT. So that's on this page. The first is track is polynomial time. Examples 2 and 3 are famous FPT problems. The fourth one is open. You want to be able to say some characterization of which problems of this type are tracked are FPT or which ones are not. So give the characterization result here. For every Boolean language gamma, we have 3 cases. Either it's FPT and the main case is coupled min-cut, or the problem is W1 hard. So that's FPT speak for saying there's almost certainly isn't FPT, like the gunning time has to be N to the K, or the problem is able to express directed cut problems. So the notion of expressing directed cut problems is a technical notion that would be too much of a detail to define here. Just so as to say, a framework of flow augmentation applies to undirected edge cuts. And I think it will be too much to ask to solve like the possibly most notorious open cut problem of chain sat at the same time as a side effect of just studying some particular CSP setting. So the third one contains tractable and intractable cases, but anything that isn't secretly a directed cut problem, we are able to calculate. And as a summary, as an essential summary in some sense of the message of this characterization, I'll define 2 relations, and we can we'll translate this into a graph setting to make it more easier to think about. The first relation of 4 variables says A equals B and C equals D, and not A or not C. The second relation is just A equals B and C equals D. So if you have min-sat with assignments and the second relation, if you turn that into a cut problem, you have an ST cut where the edges of the graph are arbitrarily paired up. So each pair of edges can be cut together simultaneously at cost 1, and there's no correlation between these 2 edges behavior at all in the cases where they are not cut. So that is W1 hard, like you can't synchronize the cut across these pairings. And a surprising fact is the problem, the other main problems being coupled min-cut. If you have almost this double equality constraint, but you add a one-side condition that out of the one pair of edges A, B, and C, D, at most 1 is reachable from S in the solution, then the problem becomes FPT. I just give a view of the cases of min-sat here, because as MSR said, I am partially from the CSP world. I have an interest in CSP, and one reason I find these dichotomy or characterization questions interesting is I always just want to know which are the tractable cases, what are the tools you need in order to handle that, and in this case, the tractable cases fall into 3 groups. One is a slightly more complex version of Edge Bipartization. One is a slightly more complex version of a problem which has been called the graph pair cut. Like you make a cut in some graph where you have to satisfy some side constraints. And the third one is a generalization of the coupled min-cut problem, which will be the main study. And the remaining cases, as I said, is W1 Harvard or directed cut problem. Out of these three cases, the first two can be solved by known methods, meaning iterative compression, branching, basically the same methods that were previously used to solve the basic versions of these problems. Coupled min-cut is more of a challenge. I feel like I should, again, I feel like I should give a second here to, if there's anyone who has questions about the CSP side of things here, because we're not going to be digging into this other than to say this characterization exists, and from now on we just focus on how a little bit about the properties of coupled min-cut, and then move on to talk about the flow augmentation procedure itself. Okay. So if we look at coupled min-cut as a graph problem, and I got some slides here from Eunjung. As a graph problem, you have a graph with vertices S and T and some budget bound K. Your goal is to cut S from T at the cost of at most K. The edges are grouped into pairs, and the rule is you can cut both edges in a pair simultaneously at cost 1. But if you choose not to cut any edge of the pair, then at most one of E and F should be reachable from S in the cut. So if you just look at this figure, so the colors of the edges are the pairings. So this is just two paths from S to T. The first one, the red edge is coupled with the last edge on the second. The second edge on the first is coupled with the other yellow edge, and so on. So there are 5 pairs, and just take a moment to look at which possible normal min-cuts are in this picture and how they correspond to trackable solutions. So the first impulse might be to just cut everything as close to the source as you can, because then you want fewer things reachable from the source. But then, of course, you're cutting 2 edges that are in different pairs. So the cost of cutting closer to S is 2, not 1. And if you cut, on the other hand, if you would cut closer to T to take the other extremity, you not only are you paying 2 to do so, but every other edge that goes before this pair becomes violated because both endpoints are reachable from S. But any one of these pairs, so any one of these 5 different pairs will be a way to separate S from T at cost 1 while also satisfying the side constraint. Like if I cut the yellow edge, then the red edge is outside of S in the lower path, and the other 3 edges are outside of S in the upper path. It's not like this. So this being the set of reachable vertices under the cut. And this is the so this illustrates, also this picture illustrates that, well, the cuts in this case form an anti-chain. So one popular approach for solving this cut problems is to try some kind of locally greedy approach, like either separate, reach as few vertices as possible from S or as many vertices as possible or something else. But this shows that there's an unbounded number of pairwise incomparable solutions that are all optimal. So a lot of the standard tools can't really work for this problem. So for a little bit, so if we just name a few properties of coupled min-cut. It's NP-hard in general, clearly. It's tractable, meaning FPT if Z has to be a min-cut. I really wish I was able to go into explaining why this problem becomes tractable if Z is a minimum cardinality as T-cut. But I chose to explain something about flow augmentation instead, and then there wasn't enough time to do both. So I should say, I don't know if it's polynomial time at the minimum cardinality case. I don't think we know that. Correct me if I'm wrong. But certainly it's not very hard to make it FPT. using some structural observations. The more interesting property or the indication for why this is might be a serious nut and not only a problem that we didn't get the right perspective on. So edge multicut, which as I said was a notorious open problem for a long time, was very difficult to solve independently. FPT reduces to coupled min-cut. You can either reduce it by a slightly trickier reduction, but still within the scope of what people had already been trying for edge multicut to reduce the directed to coupled min-cut, or you can do a much easier reduction, which is the direct iterative compression reduction from multicut, edge multicut into the generalization of coupled min-cut. So these problems are at least as hard as multicut. And now the last one is subjective, but as far as we are able to understand the problem, this coupling, this combination of coordination across different parts of the graph, like the coupled edges are not connected to each other, but you also have the side constraint of one of them should be separated from S. It makes a lot of the previous method for cut problems fail. So for example, anything that is secretly relying on locally greedy choices, that immediately fails just because the problem contains anti-chains. So what's called important separators, what's called shadow removal, fails to apply because the problem doesn't have a bounded number of interesting solutions. The decomposition methods don't apply because the presence of coupling, which is outside of the graph itself, means it's not tractable, but if you bound by parameterized by tree width, for example. The one step which we don't know how to do, but I wouldn't exclude the existence of such an algorithm, is if somebody were to sit down and do some serious study of the properties of its LP relaxation. I think the LP dual has some interesting structural constraints which might help you to get a slightly more sane algorithm for this problem compared to what we're doing. But our approach will be to solve coupled min-cut using flow augmentation. The application is definitely not straightforward. I want to say too much about its ingredients, but the idea is obviously, of course, the idea starts with trying to reduce the situation until a set is an ST min-cut. And then if you have an ST min-cut, you can guess which pairs of edges in your max flow are going to be cut by the same constraint. And then after some cleaning, you can use this coupling to reduce the search space to a 2CNF formula. It's hard to say anything more than that, but without going much deeper. So this is the most difficult part of the paper, but coupled min-cut is FPT using several flow augmentation tricks. And right. And the rest, and the last part of the talk, I will just give an idea, like an overview of how the flow augmentation procedure works. So this will not be anything like a complete proof. I apologize in advance if this is too hand-wavy, but I'll try to give the main ingredients and the main ideas. This is not actually very difficult. It just becomes technically unwieldy if you want to do it to full explicitness. Yeah, were there any questions about what I did in this section, the coupled min-cut, for example? Yeah, okay, I didn't really present the problem to an explicit degree at all. So, okay. So take a step back and think about the flow augmentation task. So a reminder, the input is a graph G with vertices S and T, a current flow, which I'll note by lambda, and a target flow K. And there exists an unknown ST cut Z our task is to add edges to G such that Z is an ST min cut. And if we make a few observations, something went wrong in the animation here. So make a few observations about what our task is. First of all, we're assuming that Z is a minimal ST cut. That means that G minus Z has exactly two connected components. I've called them HS and HT in this talk. They were called RS and RT in the paper. And the only thing which is forbidden, so if A is a set of augmented edges, the only edges we are forbidden to add are those with one endpoint in HS and one endpoint in H sub T. So if we knew what HS and HT was explicitly, we could even turn HS into a click, we turn HT into a click, and then Z is extremely highlighted as the only same separation between S and T. But of course, we don't have them on hand. So we're trying to do some guessing to maximize the probability of increasing the flow from S to T without crossing the gap, without augmenting across. So the augmentation edges are not originally present in the graph. That's why here we have to think about these partitions. It's not just K individual edges we're avoiding. We're avoiding any edge with one endpoint on the left, one endpoint on the right. So doing this, of course, we'll have to think about min cuts. So some highest level view of what the strategy is. So people who are experts in graph and connective augmentation suppose not much of this will be very new to you. This is, I think, mostly standard ingredients. It still took us several iterations of false starts to reach this version of the result. So the general strategy is we can think of tracing all min cuts or let's say we're tracing all min cuts from S to T. We're guessing for each one how Z interacts with it. And we are adding augmented edges in a way that's consistent with this guess. This is a very general description of framework. By all min cuts, I mean start from the left and work your way at S and work your way towards T. And by interacts with a cut, I mean not only whether Z contains an edge of the cut, but also which vertices of your current cut are contained in S and contained in T. So the main observation which makes the whole guessing framework feasible is for any cut C, where all vertices or all edges of C are entirely contained in one of the two components, there are no bad guesses here. Like all augmentations across between the vertices of C are valid augmentations. So what we want to do is we want to control those min cuts C where some vertices, some edges of the min cut are on the S side, some are on the T side in G minus N. In particular, we want there to only be F of K places where we have the potential of making a mistake. And then we can just, and if we have F of K guesses which have to be correct, and each guess has some polynomial in K or F of K different possibilities, of course, there will be an F of 1 and F of K probability of getting all of these relevant guesses correct. So start to talk about decomposing the graph into min cuts. It's a well-known property of cuts that they uncross, as it's usually called, so by some modularity. Like if you have a pair of cuts where that intersect, they cross each other in some way in terms of which vertices are reachable from S, you can uncross them into two cuts where one of the also min cuts where one is strictly before the other. So you can pack. This means you can pack min cuts in a graph where the first min cut is just the cut that cuts as close to S as possible. The next cut is the closest cut subject to to all all edges of the previous min cut being completely on the S side. And then you pack the third cut subject as close to S as possible, subject to being completely disjoint from the second cut. So this is just a chain of the min cuts, and this is efficiently computable with standard, well, 45%, I suppose. So that's the standard max flow computation. And we will use the term block to refer to the vertices between two consecutive min cuts. So looking at this picture, yeah, a block doesn't have to be connected. There can be, and not all min cuts are of the type CI, but at least the blocks decompose the graph, the vertex set of the graph in a clean way, so there's something to work with. And one more ingredient, we define bundles as a bundle is either a single block if that block induces a connected subgraph, or it's a sequence, a consecutive sequence of blocks such that adding one more block would make the induced subgraph connected. And if you look at this picture and think about where are all the min cuts, ST min cuts. If your graph consisted of just K completely disjoint edges from paths from S to T and have length n over K each or something, then there are basically n to the K different min cuts because you have an independent choice on each edge. And in that case, the blocks would just be sets of isolated vertices, but then your decision between where to cut has no interaction whatsoever between the parts. And as soon as you have edges connecting the different paths in some sense, it becomes the number of possible min cuts, especially since the graph is undirected. The configuration of possible ST min cuts become more and more constrained as you paths are more connected to each other. And the idea of this framework will be that we can prove that just knowing that Z is a minimal cut of cardinality at most K, there are at most some order K different bundles which don't behave extremely cleanly. Okay. So the first claim, as I said, is that at most order K bundles are affected by Z. And a definition, not on this slide, but the definition of a bundle which is not affected is to say all vertices of the bundle and also all neighbors of the vertex set in the bundle are in the same connected component in G minus N. So the closed neighborhood of the vertex set in the bundle is in the same component. That means unaffected. And that also means that all augmentations within this bundle, all of them are valid. So we really don't worry too much about making incorrect or correct guesses in such a case. And the argument for why not too many bundles can be affected is, well, if one bundle is either connected on its own or almost connected, like if you add one more block, it becomes connected. This means that if you have two bundles after one another, which are disjoint from Z, they induce a connected subgraph. And of course, if you don't do any cuts inside the connected subgraph, it must be entirely in S or entirely in T. And if before that point, you did some cutting, some separation in Z, but not complete separation from S to T, all that work would have been undone because all vertices would be reachable from S again. So the relevant bundles under this definition is a sequence of up to like 2K or 3K or something different bundles. So we can guess at the top level, we can guess what these stretches of bundles look like. We can compute the bundles efficiently, or we can guess which ones are affected and not affected. And once we know this, we can start kind of zooming in as a reviewer expressed the thing. You can define recursive new flow augmentation instances. I know I'm running towards the end of time, so I won't go into the technical details of recursion. But the idea is just that we would trace progress in a recursion by two parameters. Either we have a recursive instance of flow augmentation where Z has fewer edges inside the subgraph than in the whole graph, so K decreases, or we have managed to look at the part of G which is more strongly connected than the original graph, and then the max flow increases. And if lambda is equal to K in a recursive instance, then our task is already done because no augmentation is necessary. So just a very general idea of what do we do once we have guessed the correct set of bundles. The setup, the definition is to the left of the, so now we're just looking at the bundle being just one effective bundle. So by definition, everything to the left side will be entirely reachable from S. Everything on the right side will be entirely reachable from T. And our augmentation task reduces to this induced subinstance of adding connectivity from S to T. If you just connect S to the, if you just identify all the vertices on the left side to one and identify all the vertices on the right side to one. And there's two cases. If your bundle is disconnected, you can imagine it's easy to recursively zoom in or the augment inside only one of these connected components. Not a surprise, the parameter decreases. Otherwise, this is the most interesting case. Your bundle or stretch bundles is connected. In this case, we guess so the neighbors of the min cuts inside the bundle. We guess which of these are reachable from S or reachable from T. Two cases. Either we guess that one of the edges surrounding the bundle is cut. Like if the neighbor of one of the S vertices it has labeled T, this means we have identified one edge of Z which is going to be deleted. And then of course the recursive budget is decreased. And the second property which you can't prove, but it's a basic fact of min cuts, the way we defined blocks means if all of the inside vertices S are reachable from S, if all of the inside vertices on T side are reachable from T, you actually have increased the ST connectivity in the recursive instance. And finally, in the case where you have more than one bundle, you do basically the same thing. You select one cut between bundles. You guess on all its vertices, which ones are on the S side, which ones are on the T side. You get two recursive instances, and because your bundle is affected, it can't be the case that the entire cut budget goes completely on one side of this separation. And then you have some kind of progress. And if you want to get the best possible success probability, you have to analyze this much more carefully. But in terms of why it's possible, I think this is enough of an overview. And once we have guessed these allocations S and T, we will be allowed to just add all edges between any vertex on this picture with a label S, and all edges between any paravertex in this picture labeled T. And in addition, we also add the edges from the recursive augmentation column. And this is so this is the end of the material. As a summary of flow augmentation, it's a method of solving hard problems in FPT time by reducing your instance to one where your solution in some sense corresponds to a max flow or minimum cardinality min cut. We saw a few applications, one simple one trickier one. It's an interesting fact that the complexity of min sat gamma, the CSP dichotomy question, contains only, well, in some sense, we like to say that this was the last missing piece for being able to solve these problems in FPT time. And the main question is there a directed version of this framework? Because that would be extremely useful in settling open questions. Thank you.
Thanks a lot, Magnus, for a nice talk. So we already have a question. So the question is max cut and min KB cut. They both have p-tasses on dense graphs, and but usually cut specification is easier than cut augmentation. Could you please explain more about your results regarding the density of graphs.
I would say that we consider K to be a parameter in the sense of FPT, which means we assume that K is small. So if some part of your graph is very richly connected, like K+1 connected to itself, this will just be completely inside one of the blocks in the decomposition, and we will never try to cut through it. The other part, I'm not sure I'm asking the right question, the other part of your question which I want to highlight, I did mention that I'm assuming that Z is a minimal cut. The true setting is a little bit more general than that, but there is still a restriction in that Z is a relatively simple cut between S and T. So if you try to cut into K different parts, I would say it's probably possible to adapt the augmentation network for more than 2 terminals, but you would need to, well, you would lose some of the success probability will get worse. You would need some more analysis than we have done. So this doesn't really apply to the K-way cut question.
Does that help, Rupe? Great. There's another question from Ruhani. Ruhani asks, does your flow augmentation lemma and its subsequent applications work for vertex separators also?
No, that's probably a good question to look at. We just haven't looked at the vertex deletion question too much at all. We did spend some time before this paper, some of us working with the directed graph cuts, and they are not surprisingly extremely devious, but the vertex deletion version we haven't really thought too much about. Or, I think.
Okay. Thanks. Are there any other questions? While we wait for other questions, could you comment probably on approximation for min-sat gamma?
So min-sat gamma is I would say that it's a slightly weaselly problem formulation. You should really phrase it as what's called valued CSP, Boolean valued CSP. You should phrase your setting in terms of having cost functions instead of just constraints with values 0 and 1. So if you want to approximate min-sat gamma, the first thing you do is to take, and you have a finite language gamma. The first thing you do is to break any conjunction of constraints, any conjunction of constraints like A equals B and C equals D. You break that up into 2 separate edges and you only pay a factor 2 in the solution cost. And then you're reduced back down to problems which were studied in the 90s about approximation properties.
I see. Okay, so the arity of the constraint somehow appears in the approximation factor.
Yes, I mean, for an approximation person, if you have one constraint which consists of R different unrelated equality constraints as one bundle, this would mean that you pay a factor R in the approximation range. And that, as far as I would guess, that's probably optimal, but I'm really not an expert in approximation.
Okay, thanks. There are no other questions on the chat. Okay, if there are no other questions, then thank you, Magnus, for this very nice talk. And thank you all for attending. We'll see you next Tuesday.